If you're in year 11 and 12, you're going to be watching this to learn how to look at data to make significant improvements to the method, even if you've been moved off a gas collection method to a data logger like a temperature probe or a spectrophotometer. If you're in year 7 and 8, you may actually be using this to work out how to improve your gas collection method for your reports or exams. Now, the first major thing we need to do is to always do initial rate rather than average rate. So if you have a look here, this is the actual data from the experiment. I've just put it in fast forward for you to have a look at as I'm talking. And what you have here is you'll get a line of best fit. You get all the data points and put a line through it, so it's a nice smooth curve. And the blue line is the initial rate, the rate at the very start of the reaction at time equals 0. If you do the average rate, it'll depend on where you decide to stop. And as you can see, the gradient, the steepness of the curve gets lower and lower and lower. And so the rate gets lower and lower and lower. And so the amount of volume per time gets smaller and smaller as you move across this curve. So the initial rate is the steepest, and so that's the most volume per time, and that is the actual true answer. And so you need to take the initial rate to get the true rate, and in most cases the average rate will give you a slower rate than what the true rate is. The reason for that is the particles are becoming less and less, so there's less and less collisions because the reactants are all getting used up, and so the rate slows. There can also be issues with temperature changes, either heating up or cooling down. And so you're not controlling your variables. If you're taking an average rate, you're not controlling for concentration changes or temperature changes and even other things. So that's why you always take the initial rate. So we're going to just do initial rates for this video. The second thing we're going to look at here is when you try and put the stopper into the conical flask, there's some gas that escapes. So to mimic that, I've just taken 3 mils off the start. And so you can see when you try and draw the line of best fit here, that's the orange one, you can see that it dips a little bit at the start. And so you're sort of unclear. It could be like really bad if you do it like this, but if you're trying to work out where the tangent is initially, the instantaneous rate at 0, which is the initial rate, it's always going to be much, much less. There's no way it's going to be over here. That's way off the curve. At best, it's over here. And so it really drops your initial rate. I would say that's probably the most reasonable if I'm doing a line of best fit. All the half the points underneath, half the points above. And so you can see it's a fair bit, it's quite a bit different. And so like at time 20, for instance, there's a 20% difference or so in the volume. Now this is the instrument that can save you. It's called a pressure equalizing dropping funnel. Now, I'm not quite sure I trust some of these ones like eBay. These are the proper suppliers and it usually costs hundreds of dollars. The thing is with these things, it's all you have to do is tap it on the edge here and that'll snap. So it's not about whether you can get one for less than a couple of $100, it's whether it'll just break or not. So instead I've just created one just using a dropping funnel that we already have. And so the issue is when you've got liquid in here and you let it through, so this is completely sealed so no gas can escape. When you turn that stopcock and let it through, the air pressure that you've created, there's also be a vacuum here. So you've got this little tube that's connecting all the way up along here. And so the air can come in here to replace the liquid that's gone out, so that there won't be a vacuum, so liquid will actually come out. And then when the liquid comes out, that decreases the volume, so increases the pressure. That's equalized by the air going up. Okay, so there's no vacuum created here and there's no pressure created here. And so it's pressure equalizing, so the pressure stays the same throughout the whole system. And so dropping the liquid in there doesn't increase the pressure and it also doesn't allow gas to escape. And so that's just a cheap version, pretty much just a free version, just using some tubing and some glass and tubing to create that pressure equalizing funnel. It also is not going to break, and if it does, it's plastic and bendable. This bit could still break, which is expensive as well, but is a lot cheaper than a couple $100. Now, obviously this video is about glass syringes and they're expensive, which is probably why you're not going to be using them. So this is really to work for your reports on how to fix them and answering questions and stuff like that. I doubt you're going to be allowed to use a glass syringe. And so what you're going to do is this is just filling up the measuring cylinder with water and collecting gas as it bubbles through the water. And so the issues with that is the gases dissolve in the water, especially if it's like ammonia gas. But all the gases will dissolve in the water to some degree. The other issue is as soon as you get a little bit of gas, there's actually water vapor gas in there as well. And so that's adding to the volume. Also, as soon as you get a little bit of gas in there, the weight of the water itself pulls down on the gas because all the water wants to come out of the measuring cylinder. And so there's a decreased pressure inside that little bubble of gas you've created, which means the bubble is bigger than what it should be. And so all of those things work against getting the correct volume. The solution to that is the gas syringe. And so the other issue is if you use a plastic syringe, there's too much pressure. So you can see this glass syringe it just slides up and down. There's almost no pressure. It's not perfect. It's not the most expensive one, but it is almost no friction at all. So it will slide. So there's no friction created. That will also decrease. That'll work to decrease the amount of volume that it seems you have. So because we've worked at a range of issues with there, you need to look at your data to see what might have been happening with yours. So if it is a low pressure, I've sort of increased the volume in a decreasing way because as the bubble expands, the pull of the water will get less. And so when I do that, the data might look like this. And so the red is actually giving a slightly higher initial rate. If there's friction on the syringe or the gas is being dissolved, I've mimicked that by just decreasing it by a set value along here. And you can see that it does actually still cause a slightly less. I'll look at leakage next, and so that'll be the same graph, the same deal. So I won't go back to these graphs for that. You can see again that'll be less volume than what you should get, so the initial rate will be lower again. So it's by looking at the data that you're going to match to which method error it might be and how to improve it. So as I just mentioned on the previous data, gas leakage may look the same as either friction on the plastic syringe or perhaps even a badly designed glass syringe, not a good quality one, or the vapor, or collecting over water where the vapor is getting dissolved. So just a less in the system than you would expect. And so what I'm showing you here is how to deal with that. You just put all the system under the water. You'll feel the pressure. So the gas will be under pressure a little bit as you push it under. And so that will hopefully show all the water leak, any of the gas bubbles coming out, if there's any leaks in the system anywhere. And this one's all clear. There's no bubbles coming out in any of the parts. The fifth thing I'm going to look at is if the reaction itself releases a lot of heat, that's going to cause the gas to expand. And so you're going to get errors there. We'll look at the data in a second. So there's a range of gases that we could look at. And so I've purposely chosen this one here because it has the smallest number. So that's giving off the least amount of heat. These ones here have a much larger enthalpy value, much larger number. So these are actually release a lot more heat when they release their gas. Another thing you can do to solve it is to use lower concentrations. I've gone for, they're not super high concentrations, but I've also gone for one that releases very little heat. You can also measure the temperatures of the gas and the liquids to control that and to work out how much of an effect that actually has. But if you look at the data and you see that you're getting, maybe perhaps with the stronger concentrations, you're getting a higher initial rate than you're intending to. So I've mimicked that by just slightly increasing it by more and more, because as the reaction progresses, everything's getting hotter, so the gas is getting hotter and hotter. And so that's what the graph might look like. And so if your initial rate is creeping upwards, it may be that it's caused by the heat. Now, incomplete mixing is what we're dealing with next. You'll see here that there's a magnetic stirrer at the bottom, and I will turn that on and I'll start spinning around, and then I'll release a certain amount of volume. I'll explain that in the next bit, the volumes and concentrations. It would have been better to have put a large volume into a small volume for the mixing. But you'll see later I've already committed to my concentrations and calculations, so I'm not going to change at all. And these were the chemicals that I had that I could just grab off the shelf, so I wasn't going to spend the time making up specific volumes for that. And so what you're going to expect there, I didn't do a data one for this, but it'll be a slower rate if the mixing's not sudden as good as it could be. And so the stirrer mixes it quite well. I can actually get it to spin around the whole base in kind of a mad fashion. I didn't do it here, but I was doing it before. I could have adjusted it. And also the fact I chose to use liquids as well for the more complete mixing rather than doing a heterogeneous reaction, a solid to liquid like a magnesium solid with acid, or a calcium carbonate or sodium carbonate one with acid. So I went for liquid to help with the mixing. Okay, the next thing I'm going to talk about is getting the correct concentration and volume. So I'm just going to show you the video here of the last, I stopped after about 5 minutes. I got to about like 88 after 5 minutes, but that was really kind of crazy slow in the last couple of minutes. So I just gave up and didn't wait for it to get to the end, because that could take another 5 minutes and I've got things to do. All right, so concentrations and volumes, there has to be enough chemical. You can't just have, you've got to have an excess of the acid. If you're looking for the effect on the sodium carbonate, I think I've said calcium carbonate throughout this video, but anyway, if you're looking for the effect on the sodium carbonate, you've got to have an excess of acid. So you've got to make sure you've got an excess of that. You've also can't let the plunger fall out and break, so you can't go over 100 mils. So even though it's really slow and it takes a long time to get there. And so this is probably for senior chemistry students to be able to do the numbers, or your teacher will have to do it for you. So I've just reversed engineered that. So I just went to ChatGPT to get just a rough number, and then turned it into a nice neat number. And then looked at the shelf to see what I did have, and I did have 0.1 molar, and there's a whole heap of HCl concentrations we have, but we don't have many of these things. And so they're the numbers I used. So just checking the calculations, because you can't trust AI for that either. And so I need about, this is the number of moles. I'm going to put that many mils in. And that's telling you why I didn't do a large to a small, because I'm just using the chemicals that I have on hand. But I had a mixer anyway. And so that works out, I need this many moles of hydrochloric acid, so I need about 8 mils of 1 molar. I could have gone for 0.01 and put heaps in there, but I did mark off using 20 mil aliquots of the dropping funnel, so that I could have filled it up and just released, without having to top up. I could have just released 20 mils, and then another 20 mils, and another 20 mils. So I could do many experiments without touching that part, the top part of the system. And so I needed 8 mils, and I was delivering 20 mils, if you're wondering what I've been doing this video. And so then I was expecting that it won't go over 100 mils, and so the syringe is also safe. Okay, so there's a lot of work you've got to work out limiting reagents, most importantly, for this. And if you stuff all this up, there's going to be all sorts of problems. So the last thing I'm going to look at is if your data is all over the place, you just need to do more trials, a larger range, increasing your accuracy and precision. So a trick to that is I'm just showing you a burette. So that just allows you to accurately measure the correct volume out at the start, the amount of sodium carbonate that you're putting in. It's quick and it's accurate because it's an analytical glassware. And so if you're increasing, doing something in your method that increases the speed and the accuracy and the precision, as well as because of that, you're actually getting more done. You're just killing several birds in one stone. And so that's a good trick, using a burette to increase the accuracy, precision, and speed of your experiments. And you can see here I've got very precise data here. And so in the original one, you can see that it's a nice smooth curve. But if I get rid of the blue dots and just leave the orange, you can see if it's imprecise. You're really unsure about where the line is. You're really unsure about whether those data points are, whether that line of best fit does actually match the data, because a lot of these points, the error bars do not overlap the line of best fit. So you have a little confidence in the line of best fit and also little confidence on what the initial rate will be.